Today we are going to finish talking about stack machines. So last time we talked about how to convert a context-free grammar to a stack machine. And I'll just refresh our memory. It's a very simple procedure. You just have to remember how to do it. So for example, this grammar, S goes to A, S, B, or T. T goes to B, T, or epsilon. This one, when you convert it into a stack machine, becomes read, pop, push. I don't know if you remember the procedure. It's very simple though. Every grammar production becomes an epsilon transition in the stack machine. So the first one, S goes to ASB, becomes read epsilon, pop, S, push, ASB. And then S goes to T is read epsilon, pop, S, push, T. T goes to BT, becomes a epsilon, T, BT. And then T goes to epsilon, becomes epsilon, T, epsilon. Those are the rules. Each grammar production translates directly into one of these epsilon rules. And then we have the sort of letter clearing rule. Read A, pop A, push epsilon. Read B, pop B, push epsilon. All right? This is the procedure. It's very simple. You just have to, remember how it works. This is how you convert a context-free grammar to a stack machine. Why is it important to be context-free? Remember, context-free means that the left side of each arrow is just one single non-terminal symbol. Most of you remembered that on the test. That's what context-free means. And that's necessary for this to work because this thing on the left side is what goes in the pop column, and the pop in a stack machine is required to be just a single symbol, which is why that needs to be a context-free in order for that to work. All right, I would like to talk about going the other way. If I give you a stack machine, can you convert that back into a grammar? That actually is possible too. So we can convert a stack machine into a grammar. And this also has a simple rule. This rule is like deceptively simple, or maybe it's not really deceptive, but it is kind of so simple and not obvious why it works. But I'm going to tell you how to do it first, and then we'll talk about why it works. So, here's the short version. A stack rule, like pop, push, read. I forgot read. If you have a stack rule that's like read X, pop Y, push Z, this becomes a grammar rule. Y goes to X, Z. And that's it. If you do this for every stack rule, and you turn it into that grammar production, it works. So I want to do an example, and then we'll try and talk about why that works. But this is how you do it. Every stack rule, read X, pop Y, push Z, becomes a grammar rule. Y goes to X, Z. So here's an example. How about this is a stack machine for all X such that the number of A's in X equals the number of B's in X. This is kind of a complicated stack machine, but we did this example. The idea is I'm going to read A, pop S, push X, XS. A big X on the stack represents sort of an extra A in the string that we've read so far. A big Y would represent an extra B. And they kind of cancel out in the sense that if I read an A and I see a big Y, then I push an epsilon. We did this example a couple weeks ago maybe. It's not so important that you remember how exactly this is supposed to work, but the idea is extra B's in the string end up producing Y on the stack. Oops. BY gives you another Y. A B and X kind of cancel out and give you epsilon. And then finally we have this epsilon S epsilon rule that you have to use at the end when the stack is when all the X's and the Y's have canceled out, evened out, you end up with just an S by itself, and you use that to finish. All right. Now, for the sake of this example, I'm going to give these numbers 1, 2, 3, 4, 5, 6, 7. All right. And So this is the stack machine. It's not super important that you remember this example, but I'm trying to demonstrate this procedure here. What I said, a rule, sorry, it doesn't quite all fit on the screen at once. A stack rule like read x, pop y, push z becomes a grammar rule, y goes to xz. So the grammar, an equivalent grammar is S goes to AXS. This is going to look very weird. I'll number the steps in the same way. X goes to AXX. I'm each time doing this. You take the one in the middle, you make the arrow, and then you stick the other two together. So S, which is in the middle, goes to A times XS, like that. All right, and so on. The next rule says, rule 3 would say y goes to just A. That would be A followed by epsilon. Rule 4 would be S goes to BYS. Rule 5 would be Y goes to BYY. Rule 6 would be X goes to B. And 7 would be S goes to epsilon. All right. We are just doing this simple thing every time. The middle one goes to the first one followed by the last one. All right? So this grammar has 7 rules. If I were to write this in a more traditional sort of compact way, would be to gather together. You know, S goes to ASX or BYS or epsilon. I just gather together all the productions which have S on the left side. That would be number 1, number 4, or number 7. Right, and then X can go to AXX or B, right? And Y goes to BYY or A. That's the idea. And there's your grammar. And it turns out that grammar is equivalent to the stack machine. It's a simple procedure to construct. I want to talk about why it works, though. It's not obvious to me, at least. It's not obvious at all why this works. To get there, I want to let's look at some example derivations. Let's derive ABBA I want to derive it on the stack machine, and then also on the grammar, and see if we can see any relationships between how the stack machine works related to how this grammar works. So let's do it on the stack machine first. Remember, on a stack machine, we begin with our string, followed by S on the stack, and then we do some steps. Now, in this case, the stack machine is kind of unambiguous. I think there's more or less going to be only one step that we would choose from each time. We're not going to use the last step, step 7, until the very end. But A, B, B, comma, S. My first step, I'm going to do rule number 1, which is a read A, pop S, push X, S. Anybody remember how to do this? What should it be after you do rule number 1 here? I'm actually going to label it. What do you say? Yeah, what goes first? BBA. Yeah, BBA and XS, he said. Right, great. Okay, next I'm going to do a read B and pop X. That would be rule 6. Rule 6 is read B, so one of the B's goes away, and then pop X, the X goes away. So it's BA, comma S. Next, I think I'm going to do rule 4, which has a read B, pop S. So number 4, what remains will be A and YS. All right, then rule number 3, right? Because I have a read A and a Y on the stack. The A goes away, I have epsilon. The Y also becomes an epsilon, and it's just going to be epsilon S. And then finally, I do rule 7, and we're all done. Epsilon, comma, epsilon. And it's over. All right, so ABBA is accepted by the stack machine. All right. Let's see, how do you derive ABBA by the grammar? When I look at the grammar, actually, the grammar steps are much more complicated. I mean, it's hard to just look at them and wrap your mind around exactly what those steps are supposed to mean. But I'm going to try to do the same string with the grammar. And my advice is just do the same steps in the same order. This is why I gave numbers to everything, so that you can see very clearly how everything lines up. Of course, in the grammar, you start with S, But I'm going to do rule number 1 in the grammar first. Rule number 1 is S goes to AXS. So, all right, AXS. All right. Next, I'm going to try and do the same steps that I did on the stack machine. Next would be step 6, what I did on the stack machine in this place. Step 6 is this one, which is X becomes B. Okay, so I go A, B, S. All right, that was step 6. Next, just copying the derivation from before. Next should be step 4, which is, on the grammar, S goes to BYS. So I have AB and then BYS. All right, that was step 4. Next, I'm going to do step 3, just copying my old grammar steps. Step 3 is Y becomes A. And so that's going to be A, B, B, A, S. And then finally, step 7 makes S go to epsilon, A, B, B, A. All right? The same grammar steps in the same order do the same derivation. All right? I would like to try, I want to be able somehow to look from this stack derivation to this one and say, yeah, those are basically doing the same thing. Although when you look at them written out, they don't really look exactly the same. For instance, after step 6, this one says ABS, this one says BAS. What exactly is the relationship? Or after step 4, this one says ABBYS, this says A and YS. Can anybody say what the relationship is between these individual steps and these steps here? Yeah?
For the grammar, you're going from nothing to a string, and then in the stack, you're going from the string to an empty.
Yeah, so in the case of the first part here, the string part, at least on the stack, it starts off with the whole string and it shrinks down to nothing. Whereas here, it's kind of the opposite. Here, we start with kind of nothing there, and then it grows and grows and grows until you have the whole string. All right, so in the stack machine, the first part of the pair is always the string which has not yet been read, right? Whereas on the grammar, the first part is more like the part of the string which we have already read. And then, can anybody say what is this part, the other part of the grammar derivation? How is that represented in the stack derivation? Is there a relationship? Yeah? Yeah, that part. The second part in the grammar derivation, the first part is the string as you're building it. The rest of it actually is the same as the stack from one step to another in the stack machine. So can I say something like this? Our grammar steps, I'm trying to explain why these are actually the same process. Our grammar steps always look like, you can kind of break them down into two parts. There's the sort of the string read / built so far, followed by the stack, right? Where this is like the part which I was underlining in red, and this is the part which I was underlining in black. As you go through the grammar derivation, every time those strings, you can break them down into the first half, which is the part of the string which has been read so far or built so far, depending on how you want to see it. And then the second part of the string that you see there is what you see on the stack from step to step. All right, and then all the action, every time you do one of the grammar productions, I'll say the action happens right here, right? Every one of the productions, if you look from one step to the next, what changes from one step to the next? It is sort of in the middle between the red part and the black part there. The red part grows a little bit, and then something happens at the leftmost side of the black part there. All right, that's where things change right in the middle. All right, and specifically, can we say what exactly is the action? So what action precisely? Well, if the rule is like this, if the stack rule was, read, pop, push. If the stack rule was x, read x, pop y, push z, then something like this. There's the string part here. Let's imagine that there was a x. Let's imagine that y was on the top of the stack. If y was on the top of the stack in my grammar derivation steps, I have some part of the string so far, and then the stack part looks like y, and then like whatever else is on the stack, all right? Then this will become, if I have a portion of my grammar derivation like this, doing the underlines as I usually do, if the string part is just some part of the string, and then I have the stack part, which has a y on the top of the stack, if I do that operation, read x, pop y, push z, what does that turn into? Well, when you read x, that means x gets added into the string part, so it becomes whatever that string part was before, but with an x added onto it, right? And then the y goes away and is replaced by a z on the stack part. So it becomes like this, and then some more of the stack part. All right? If that's your stack rule, read x, pop y, push z. The y goes away and turns into a z on the stack part, and on the string part, an x is added onto the rightmost side because you just read the x, and so now you do include it in the string which you have read so far. Anyway, you can see though now what happens, like what exactly is the substitution here? So this was a grammar substitution. Y turns into xz, right? That's exactly what happened. So the moral of the story is, when you do a stack rule like this, the effect in the grammar is to do this substitution. This y turned into an x followed by a z. And this is why all of this is valid, right? When you do one of these stack rules, read x, pop y, push z, the effect in the grammar is to substitute. Instead of y, it turns into xz, all right? And so this is why that general procedure is correct. If you translate these lines into a grammar, they must translate like this. Y becomes xz, all right? All of that somewhat long-winded business trying to convince you that all of that is valid. All right? Yes?
So why do something like that over what we had done before last week with epsilon?
Yeah, these are actually two converse operations. So last time, I was about to summarize this, so this is a good little segue here. Last time we discussed how to last time was converting a grammar, in particular a context-free grammar, into a stack machine. All right? This time is the other way around. This tells you how to, starting with a stack machine, like if you already know this stack rule, it turns into this grammar rule. So that was context-free grammar becomes a stack machine. This time, these are two different procedures, but this is how you convert a stack into a grammar. And in fact, it will be a context-free grammar just because of the way the rule works here. There is only a single symbol on the left-hand side of the arrow when you do this process. And so when you convert a stack machine into a grammar in this way, you guaranteed you are always going to get a context-free grammar. All right? What that means in a theoretical point of view is the languages which you can accept with a context-free grammar is the same as a stack machine because you can convert from one to the other, and also you can go back and forth, right? So that means, so context-free grammar and stack machines have the same set of languages. And they are called the context-free languages, so we already have a name for that. It has the same capabilities. So I'm going to write this as a theorem here. It says L as a language is context-free. Remember, that means it has a context-free grammar. If and only if L is the language of some stack machine. right? So the stack machine is kind of the machine version of context-free, in the same way that like the machine version of a regular language, the machine for that is the NFA or DFA. The machine for context-free language is a stack machine. All right? A language is context-free if and only if it is the language of some stack machine. All right? I want to refresh your memory of a picture that I drew a while ago, which is sort of like the hierarchy of languages. There's the regular languages, which are the most simple ones, and then there's this sort of larger universe of context-free languages. And of course, an example of a regular language would be something like, and a language in there would be like A to the N, whereas a context-free language would be like A to the N, B to the N. These are like universes of different languages. A to the N, B to the N is a context-free language, all right? And for regular languages, you have NFAs, DFAs. Those are the machines that give you regular languages. For context-free languages, you have stack machines. Those are the machines that give you context-free languages. We are just about done at this point focusing on this part of the universe. You know, at this point, and from now on, you should regard regular languages are like the very, very simple ones. Context-free languages are more complicated than regular, but not so complicated, right? And then we're going to talk for the rest of the semester really about out here, things which are not even context-free languages, non-context-free languages. And there are actually, in the remaining weeks of the semester, we're going to talk about 2 more sort of big circle hierarchies outside, and there's still stuff beyond that we're not really going to get to. But can I just ask, first of all, are there any simple non-context-free languages? Actually, there are non-context-free languages which are still fairly easy to describe. And the classic example of a non-context-free language is that A to the N, B to the N, C to the N. It turns out we never did any examples like this with a grammar. I don't know if you ever wondered, is it possible to do like balancing with grammars to balance 3 things at once rather than just 2 things? A to the N, B to the N, you can do with a context-free grammar by balancing. But what about trying to balance 3 things at once? It turns out, actually, this is not possible. Not context-free. Is not a context-free language. I should put not a context-free language. You cannot make a context-free grammar for that thing. We might here's some failed attempts. It's nice to kind of try to play around with this. Can you make a grammar that balances those 3 things together? A to the N, B to the N is like this. This, everybody knows how to balance just 2 parts would be like that, right? A, S, B, or epsilon. You make it so that the A and the B are created at the same time. That ensures you that there's always going to be the same number of A's and B's because they're made together in the same step. Could we try to do for A to the N, B to the N, C to the N? I suppose maybe you could try like this. S goes to A, S, B, C, or epsilon. Would that do it? No, because I already said it's impossible. But what can somebody say? What doesn't do it about that? Yeah, this one makes. They're sort of in the wrong order. It makes this, right? The BCs come together. You could get something like A, BC, 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 but that's not A to the N, B to the N, C to the N. That's something else, right? It's A to the N, BC to the N. So this is a bad idea, or maybe at least not a great idea. I mean, something else you might consider, A, S, B, S, C. How about that? Then, I don't know. Is this really going to work? Let's just do like a quick little derivation. If I go through this once, I go A, S, B, S, C, and maybe I'll do it again. There's 2 S's there. I might as well do it again both times, right? I go A, and then the first S becomes A, S, B, S, C, And then I'm like, that was this S, right? Now I do B, and then I'll do it again, A, S, B, S, C, and then I had the C at the very end. And then if I make those S's epsilons, what do I end up with? A squared B, C, B, A, B, C squared. This is definitely not what I was looking for, right? They're all in the wrong order. Like it is true you have the same number of A's and B's and C's here, but they're all in this weird order. So that's also not going to work. It turns out, you got another idea?
Yeah.
Another bad idea? I mean, it can't work, but yeah, what else?
Could you do S to A, S, and then maybe T, T, and then have T go to B or C?
Okay. I would say the problem with this is there's nothing, like you could make both of the T's become B, and then they're not going to be balanced. It might occur to you to instead say, oh, okay, then how about this? Make that one go to B and the other one go to C. But this now is the same as that, right? So it's good to try and play around with this. It turns out to not be possible. Now, unfortunately, this is something that we would ordinarily when I teach this class, usually I would go through and talk about precisely why this one cannot be done with a context-free grammar. But because we've missed so many classes, I'm gonna postpone this and maybe never come back to it. But if we have extra time at the end of the class, because what we're going to talk about next is Turing machines, and I want to make sure that we really get to cover those in detail, because that's really some great stuff, is the Turing machines. So I will say later, maybe never. We'll show precisely why A to the n, B to the n, C to the n is not context-free. It'll take maybe 2 times to, like there's a fair amount of theory that needs to be developed in order to see why this is true, and might not happen. We'll see. All right. For now, I would like you to just take my word for it that A to the n, B to the n, C to the n is not a context-free language. I thought just for fun, actually, here is a grammar for A to the n, B to the n, C to the n. Check it out. See if you agree with me. S goes to A, S, big B, C, or A, B, C, or epsilon. CB goes to BC, and little b, B goes to little b, little b. This is not context-free because the left side of the arrows are not just a single letter. And if you're like me, I was feeling good when I wrote the first line. As soon as I see this on the left side, I say, oh man, I have no idea what that is about. Like, I know what it means, but it's very difficult for me to visualize or have any kind of predictions about what kind of strings this grammar can generate. Just because when you have that weird stuff on the left side, it's like a totally different game in terms of figuring out how to derive strings with this. But actually this one, if we spend a moment or so, this one is not so hard to decipher. If you look at, let's just try an example derivation here. S goes to, well, let me just say my interpretation, if I were to say like in words, how I would interpret these two words, these two productions. The one in the middle there, I would say B can commute with C. Commute is, the mathematical word for rearranging the order. So this means whenever you see a big B and a little c, you can rearrange the order of them. And then the last one, my interpretation of this is that big B can become little b if it's next to another little b, right? That's what that rule means to me. it has a little b followed by a big B can turn into two little b's. That is the way I think of that rule, is just the big B turned into a little b. But you're only allowed to do that when it's already next to another little b. Anyway, to do a derivation, let's try to derive, say, a squared, b squared, c squared. I'm going to do the first rule first. S goes to AS, B, C. And then I'm going to do the S goes to little a, little b, little c. It becomes A, ABC, big B, C. All right? And if you wanted to do higher powers of A, B, C, you would just do that rule several times before choosing the little a, little b, little c. And now this is not like a full derivation yet, because I still have this non-terminal thing here, the big B. And I think you might agree, the only way to make this big B into anything terminal is to move it past this C and then use this rule to turn it into a little b. So this big B, it will eventually turn into a little b, but the only way you can do that is by moving it past the C's and put it with the other, like with its other little friends. So I'm going to do this CB becomes BC, right? That's the middle rule. And then the big B is now next to a little b, so it can also become a little b, and we get A, B, B, C, C. So this is how this grammar works. It's very clever. This is the kind of thing that I probably would not come up with this on my own, just because I'm very unused to writing any grammars that are not context-free. But this sort of commutativity rule is what's being used here. All right? Very cute grammar. I present this as sort of an interesting curiosity. I'm not gonna ask you to make examples like this on the homeworks, just because we're not really talking about it in detail. All right? One thing to mention, we got about 15 minutes left. Usually I say, like, something which is not context-free is in my opinion totally crazy. Although they're not always very crazy. This language is not totally crazy. It's just the grammar has to be a little weird. It is also a fact that most real-world programming languages are not context-free languages. Remember we saw I showed everybody the grammar for Python. Most real-world programming languages are not context-free. Actually, even Python is not. I showed you that grammar. That grammar was, to some extent, being slightly sneaky. There are parts of the Python grammar, the official Python grammar, which are not context-free, and I want to try and show you why. Most real-world programming languages are not context-free. Actually, any language which is capable of doing this kind of balancing of more than two things is automatically not going to be context-free. This is because Python, the Python interpreter, or compiler, if you want to use a compiler, must analyze and balance more than two things at once to parse indents. Everybody knows indentation is important in Python, and if you indent things wrong, it causes errors, or it causes your program to act differently than you thought it was going to act. Python is very big on matching levels of indentation. So a typical Python program, Python is indented in blocks like this. You know, a Python program, like, structurally might look something like this. Where that was an indented block, and then you can even have like double indented. So these big T's are meant to represent tabs, right? Those are like indentation tabs, right? Or it could look, just like a piece of a block would look like this. Where these X's, of course, are like other Python commands, right? I don't mean literally just X's, but the T's are all the same, right? They are just tabs. And every tab in Python is the same. All right? But if you read these Python programs as if they were one giant string, including like new line characters or something like that, right here, what we see here is we have something like that big program read as a giant string basically looks like t squared with some stuff, and then another t squared with some stuff, and then another t squared with some stuff, and then another t squared with some stuff, right? And the Python parser, the Python interpreter, is required to make sure that those indentation levels are the same every time, all right? Or else you have an error, or else at least the Python interpreter has to keep track of these indentation levels and match them up, keep them balanced in its own internal, parser. But that is not possible for context-free language. This kind of balancing of several pieces in between other pieces that all are required to have the same exponents. All right, this can't be done in a context-free grammar. You can't do this in a context-free language, all right? Because of those matching twos, right? It has to be able to match twos or maybe match them all threes or fours or whatever, depending on what the indentation level is. You can't do that in a context-free language. So what does it say in the grammar that we looked at? Actually, I don't know if you remember this. We only looked at it just for a moment. In the Python grammar that's published that we looked at several weeks ago, it said something like, there was something like def, and then a name, right? This is like the function definition, and then some variables in parentheses, and then the colon. And then it said something like this, indent, followed by block, followed by outdent. This is how this is described in the grammar. And you will notice that the grammar treats the entire block as a single thing. The block is not treated as like tab, 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 followed by commands, followed by tab, 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 followed by more commands. When they wrote the grammar for Python, they did not consider the tabs as like an individual part of the language, even though they really are. So, and of course, there is no such thing as outdent on your keyboard or something. Like there's no reverse tab. So the grammar, like technically speaking, the grammar that we were looking at for Python was not exactly a grammar for the language as it is typed letter by letter. It was more like a grammar for the structure of the language, but not technically the grammar for the language as you actually write it. Because there can be no context-free language for the true grammar of Python. All right, I thought that was kind of interesting. Not terribly, I would say, again, just like reading the grammar in the first place. This is not terribly important for a typical Python programmer. It only matters if you are trying to write the Python interpreter or something like that, which I've never done that in my own personal life. I use Python all the time, but I do not write compilers for Python. Any thoughts about that? No offense to you if you wrote the Python interpreter or something like that. It's harder than anything that I typically do.
Is it outdent when you back that?
Yeah, which that's not a real thing. I mean, everybody knows what they mean when they say outdent, but you do.
Combination goes back like keys.
The delete button.
No, it's like shift tab goes to that back.
But that's not that doesn't make a character. Like there is no character called backwards tab, is there? Bat.
There's no one key. You guys have
Just the shortcut.
I mean, yeah, you can do it on your keyboard. You can also hit the left arrow and it'll, yeah. But that's a little different from, there isn't actually a thing called outdent in the language. Yeah. All right, we got 8 minutes remaining. I think this is all that I want to say, at least for now and maybe forever, about context-free languages and non-context-free languages. What I would like to talk about is I'll give you a little introduction to Turing machines. In my opinion, this is like the grand finale of the course, although, I mean, the course is not over yet, but this is the what is, in my opinion, the most interesting, also maybe the hardest type of machine to make, the culmination of the ideas that we've been talking about so far in the class. I want to tell you a little bit about kind of some history about this, and then we'll get down into the details. I suppose I will get down into the details in about 15 minutes when I start recording the next thing before I go to Hotlanta. The Turing machine. So I want to sort of set the stage. In the early 1900s, I would say like right around the turn of the century, all of mathematics was being reformulated in terms of axioms. Rewritten using axioms. Axioms in mathematics have been around for a very long time, starting, I think, with Euclid doing axioms for ordinary plane geometry. But it was thought for most of the history of mathematics that axioms were a thing that you use in geometry, but you don't really do axioms. Like when you took your calculus class, nobody ever started with, okay, we got to learn the axioms for calculus. That's just not a thing that people talk about in calculus. Although around this time, it was being decided that we should try to do axioms for everything. And in fact, there are axioms for calculus. It's just your teacher never told you about them because they're super complicated and they're not very helpful in understanding calculus if all you want to do is like take derivatives of things. The axioms are not helpful in that sense. But axioms, for example, in the 1880s, is when axioms began to be used in algebra. If you've taken our abstract algebra course about like groups, you know that axioms are a big deal. You probably, in our linear algebra class, you probably talked about the vector space axioms, which were 10 axioms for a vector space, and you probably thought like, I don't like this or something. I don't know how you felt about that, but it is a fact that all of linear algebra, everything you ever do in linear algebra can, at some level, be boiled down to the vector space axioms. So that happened around that time. In the 1890s, there was a new interest in axioms for geometry that was done by Hilbert, who's a very important figure. Hilbert geometry axioms. It was realized that actually there were some serious errors in Euclid's geometric formulation that Hilbert more or less corrected. And then in the right around the turn of the century, axioms for set theory. Set theory had sort of just been invented and was becoming very popular. And nowadays we know, like you all know, that basically all of mathematics has been reformulated in the context of set theory by now. But axioms for set theory had come about. And it was a natural question for people to ask. Could there somehow be like axioms for everything? Everything. Could there be some kind of like maybe 5 or 6 axioms for all of mathematics, that everything that you would want to could be expressed in terms of just axioms? And a similar question, or a related question to this, is, can all facts, mathematically at least, be proved based on axioms? Or are there some mathematical facts for which you can't really prove them from axioms? And I would say, you all have been around the block as far as mathematics goes, and your intuition, I think, and my intuition also, is I feel like any true fact mathematically should be provable based on axioms. Like if it was not provable, why would I even call it true? Like that's kind of what mathematics is about you only call something true if it is provable. In my ordinary life, I don't actually behave in this way. Like I believe that it's true that my wife loves me very much, even though I can't prove that scientifically and certainly not mathematically. But at least as far as mathematics goes, I like to think we only believe something because it's true or because it's provable. That's kind of what the word true means. Can all facts be proved based on axioms? What this leads you, though, if you believe that all true facts can be proved based on axioms, what that means is that you could somehow write down a list of maybe 5 things or maybe even 100 things that you take as the axioms, and then every true fact is simply some kind of rearrangement of those axioms in some ordering. And that's what every proof looks like, is some rearrangement of the axioms in some order. What this means, if you believe that all facts can be proved based on axioms, the natural next question to ask is there one single master procedure to prove stuff from axioms? If it's true that all things can be proved from axioms, that kind of means that anything should be able to just be proved kind of by brute force, by just rearranging the axioms in all possible orderings until you get a proof of the thing that you're looking for, right? If it really is possible to axiomatize all of mathematics, then it would automatically be possible to brute force prove anything that you want. And this, I would say, from a mathematical point of view, is kind of disappointing to think that all of the work that is done in human history to deduce and prove facts in mathematics, is all of that just some kind of turn the crank on a machine and you could do the same thing just by brute force? I like to think that mathematicians who prove things are having some sort of leaps of creative genius, right? Or something other than just simply recombining, reshuffling axioms, all right? This is the landscape that Turing stepped into. So Turing, I know it's time to go, I'm just going to say for a moment. Turing had the idea to turn all of mathematics into some kind of mechanized procedure. And this is how Turing came up with the idea of a single machine that in principle can do anything, which is very different from other purpose-built computing machines that existed at the time. Turing had this idea that maybe there could be a single, he called it a universal machine, that can do anything, not just having a specific task that it's built for. That, of course, is what a real computer is. The whole point of a computer is that it doesn't have a particular task, but in principle it can do anything. So this is what Turing machines, this is what his basic idea was trying to come up with. And watch the video. We will have homework due after I come back next week. You can. I'm going to post the video tonight, but you can watch it whenever you like before our next meeting on Tuesday. See you then.